All right, we're recording, ready to go. That's fine, Monday. So you guys what we're doing here now. I've got about 2 or more hours of activities that I've condensed down to 90 minutes today, so I'll do my best to squeeze this in. But let's take a look at another side note is Google Meet has been especially cranky today, so I'll do my best to refresh it and keep that going, but see what we can do there. So this week, today, I'm gonna finish putting the zoetrope together with you guys. Okay, and then show you guys some stuff on reflection, refraction, optics, some demos, some stuff I normally do as labs. I kind of, you guys will see. Tomorrow we'll do some more activities, including I want to blast off some bottle rockets at the end of class tomorrow, so we'll do that. We'll do a second music day on Wednesday, and that'll be the last day for seniors. Then Thursday, want to take a bunch of stuff and try to condense it down to 90 minutes for thermal materials, and well, we'll see where we are from there. All right, here's a more detailed list of what I want to do today. Actually, got exactly through this, but like I said, I'll go through like a faster pace than I normally do this because that's how we're doing today. All right, so zoetrope. Now, quick reminder, if you're online, right, here's the final product. Is what we're looking at. Oh, hold on, what's that? Okay, right, here's the final product we're looking at. Looks like the cylinder. Give this a spin. Look at the top, it just looks like a blur. But if you look through these windows, right, then that creates a strobe effect, and then you can see. You should be able to see like a cat running on this one. That's what this is. Okay. Let's go back to projection. Oh, is this not ready for that yet? Okay. Then now where you guys should be right now is you should have your 2 zoetrope templates. Okay. I did recommend that you cut out these windows over the weekend. So if you have, then you're maybe a little bit ahead. If you haven't yet, then go ahead and cut these windows. Okay. Now, possible that they might be at a little bit different place, but that's right. Okay. So I do want to take a couple of volunteers here in just a few minutes. So hang tight on that. But if you want to volunteer, because as I was walking around the room, glance at what you guys have so far, then some of you guys have some really cool designs. Okay. Now, before I do that though, I do want to show you guys next step would be after you cut out your windows, which you may or may not have done at this point. Okay. Then I want to glue these together. Get this going. Yeah. I do not. Yeah, got some food. Yeah. Think zoetrope. Oh yeah, just around the room. You guys have some really cool designs going. Okay. So I've got my windows cut out. Okay. The next step would be that I want to glue these together to make a very long strip that's eventually going to come around to the cylinder. I want to glue them like this.
How do you go about cutting your windows?
Okay, so there are different techniques you can use to cut the windows. Right? What I did was I just stabbed the scissors through and just carefully cut out a rectangle from that point. Right? Another thing you could do is you could bend it down like this and then make an incision. It might be a little easier to cut. Now, if you do that, then you might look like a crease going across, which could be okay. It's not going to ruin it. Just, right? A third way you could do it is you could cut all the way from the edge like this. Now, of course, if you do that, then, well, you get a bunch of like floppy finger looking pieces on this paper. That could then be solved by taking a strip of paper and putting it across the top like I have on this model, right? Which actually the reason I put the paper here on this model is because I used regular paper instead of cardstock, so this made it a little bit more solid, right? But yeah, could also use it for that purpose. Okay, so there's different ways to do that. Okay, now I want to glue these together, so I'm going to take some glue. Right, right before I put the glue on, I want to think ahead a little bit. These window spacings, I want them to be equally spaced across this gap. See, if I glue them like this, then I've got these windows spaced a certain amount, but then when it hits this gap, suddenly that spacing changes. Well, that would not be good, or they could be too close. Like that would be too close together. So I want the spacing to stay even. So maybe I'll break out a ruler and I'll measure what is the center to center spacing on these windows. Right now on my template, I should tell you guys my template is a little bit different than yours. I have 10 frames, you guys have 12, but on my 10 frame template, the center to center spacing looks about 5¼ centimeters. So I will want to keep that consistent. Now here's where I was saying think ahead a little bit. So there's the spacing I want right there. Is notice it covers up one of my animation frames a little bit. If you run into that issue, then what you want to do is what I'm going to do right here, which is actually cut off a little bit of one of these windows. Or sorry, just cut a little bit of a paper off here with a card, right? So that it does not cover up your animation frame. Yep.
This one has plastic on it.
Yeah, maybe one of those like this. Like that's right behind you.
Yep.
Yeah, there. Okay. All right. So now take a little bit of glue. Throw it down. There. All right. We want to look for an optimal amount of glue, right? So just enough, but not too much, because if you put a ton on there, then it takes forever to dry. So there's an optimality, right? Not too much, not too little. Right. I like Goldilocks. This Goldilocks is probably a calculus for children. Maybe that's what that story's about. All right, so let me get this window spacing exactly right. Remember, I know I want the spacing to be consistent. Oop, that's a little bit too far. Let's see, probably right about there. That's window spacing I want. Make sure this is all straight and even. Looks pretty good right there. All right, so now I'll press this down. And because I used an optimal amount of glue, that should dry within about 10 or 20 seconds. Right there. All right. So I'm going to leave that there for a moment to dry. While I'm doing that, and I know that everybody's at a little bit different point because some of you guys are cutting out your windows at this point. Some of you guys are up to the stuff where I am. Right? Does anybody want to volunteer what they have for the camera? Yeah. Yeah, so this one is Morrigan's, and I'm glad she volunteered because this one is really cool looking. Got Pikachu running. Look at that. All right, yeah, that's right. Looped animation of a running Pikachu. He's always running towards you. All right, thank you. Who else wants to share theirs? I think quite a few of you guys have some pretty cool ones. Anybody else want to share theirs for the video? Unmute. All right, so here's what I do is I'm just going to go ahead and put this together. And if you're a step or two behind, that's okay. It's not going to be a big deal. Right? I should say, if you're at home, one of the materials we're going to use at some point is string. And if you do not have string, then that's all right. Just make as much of the zoetrope as you can and photograph that and upload that to Focus, and I'll give you guys credit for that. Right? But we'll enter a string pretty soon. Now, I do want to wrap this around into a cylinder. Again, if you're a step or two behind, no biggie. Just work at your own pace, and everything's going to be all right by the end of the class. Now, I do remember that I don't want these animation frames to cover each other up, so I'm going to make a little notch right here to make sure that that does not happen. All right, now I have to go about like this. So I want to throw some glue. Let's see, it has to be on the back side of this one, probably right about here. This glue would go. Ooh, all right, maybe put too much, but all right, oh, work. press down pretty good. Right. And then again, remeasure the center to center distance between these two windows, these adjacent windows. Remember, I want to keep this distance consistent all the way around if I can, pretty close. That looks kind of hard to do with two hands. Sometimes I envy the octopus. But that looks pretty good, I think. Oh, that's straight though. All right. Did that work? Hold that there. Yeah. And all right. All right, so I think I'm probably a step ahead of you guys, but we're right. So I'm ready to start stringing this thing. Now, I should probably show you guys the model again. Remind you guys how I string this together so you guys can see the final product. This looks like, there are different ways you can string this up, but I found one way that works particularly well. So that, well, if you string up this way, then it could probably stay good for a few years and not get warped. Like this one's a few years old. It's just made out of regular paper, but it's held its form pretty well. So see what I'm going to do is I'm going to tie a loop of string around right here. Right? Then take this over to the opposite side and tie it on the opposite side window. Right? Then if I do that for all of them, got like pairs of opposite side windows. Then see how I can bring this together, tie this together in a knot here that's on the vertical central axis, so I can spin this thing. Right? And see how this looks like a cone? So these strings make like a cone shape at the top, like a cone shape. Okay? So yeah, that's how I'm gonna tie it. And so back over here. Okay. Now if you're in class, then you probably have some string on your desk that looks about like this. Right? And it's 8 meters long, which should be plenty of string to work with. Just trying to get this not tangled though. I'm off camera here. Okay, so get some string. Now I want to remember that I have 10 windows, but you guys have 12 windows. That means I'm going to have 5 pairs of string versus you guys are going to have 6 pairs of string. Maybe I want them to be all about the same length. So probably cut about 40 centimeters or so. That should probably be pretty good, about 40 centimeters. You want to do 40, 50 centimeters. If you want to measure it with a ruler on your desk, that might be a good idea. I'm just going to cut these all at the same time next to each other, so they're all kind of the same length. 40, 50 centimeters, somewhere in there. So there's string number 3. There's string number 4. String number 5. Okay. And of course, you guys in class, since you have an extra pair of windows, you'll do 6 of those. At 5, you guys have 6. All right, so now I'm going to tie strings around these windows, just like I showed you guys. So these windows actually have 2 purposes. One purpose is to create that strobe effect when it's spinning, so it's not just a blur of animation, get that strobe effect. And the other purpose is using them to tie the string around. There you go. Okay. Now, if you drew your animation frames upside down, which sometimes I have a couple of students that do, then that's all right. What you can do is just punch some holes on the opposite side, go like punch, 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 and do that all the way around, and use those to tie the strings around. And then you can actually use the windows that are already there to still create the strobe effect. You can just view it from the underside. It's like hanging from a tall ceiling. Imagine it like that. And so there's one place I've tied it. Just go to the opposite side. All right, opposite side window right here, and tie this around there. Okay. Ooh, it looks like I made the string just long enough. Like I wouldn't want it to be any shorter than this. It can be too short, but it can't really be too long because you could just tie it off somehow else so that's all right. Right. So if you're worried about it being too short or too long, then definitely err on the side of too long, because sort of is no such thing as too long. You can always amend that, but too short might run into some trouble. Right. And mine are just at the point where I wouldn't want it any shorter. All right. Okay, so 1 down, 4 to go. All right. Like that. So kind of hang this like a pail. See how that's going to go. All right. All right. So string number 2. All right. And opposite side window. All right. So 2 strings down, 3 more to go. String numero 3. Making that square knot right there. All right, opposite side. Probably at least, if you go 50 centimeters, that's probably pretty safe. But let's call it 50. If you do 40, then you're probably good. I think mine are closer to 40. But 50 centimeters should probably be pretty good. 50 centimeters. Okay. This way, if you're on the long side, then quick fix at the end. Once we tie these all together into like a cone shape. Okay. Here's 3 strings. Refresh and okay, back on Google Meet. Oh. All right, so now I have all these strings tied. Okay. Now here's where I want to grab all the strings. Okay. Remember, each of them individually is like tied kind of like a pail handle, something like that. Okay. But I'm gonna bring these all together into a cone shape. Okay. Now maybe I'll do this off camera, but I'm going to give it a spin around its vertical axis, and I want to make sure it's balanced.
right? And then all the strings are kind of taut. If there's at least one in there, then you're right. It's not gonna fill it, but gives a spin off screen. Okay, so that looks pretty good right there. All right, so off screen, I just spun this into, well, you see where these strings are coming around like a cone, right? Now, I have kind of a flat cone on mine, but that's all right. Right, so this cone, right, works. Okay. Then we gotta tie these off right here. So see if I can do this in front of the camera. It's kind of tricky because made this just barely long enough for this to work. All right, gotta tie a knot right here, right at the top. All right, make sure this is still balanced. So while the knot is being tied, again, sort of shift this to the central point. All right, I think it looks pretty good right there. Just a spin. Oh yeah, that's gonna work. Nice spin right there. Nice. There you go. Oh, actually, there's one last step. Is what you might want is maybe an extra string that you can hold it from, because otherwise this is a real short place to hold it. Okay, so I'm gonna cut off one last length of string. Has just a few centimeters long. I don't know, maybe 10, 20 centimeters. About 20 centimeters. Just to create a handle I can hold on to while this thing is spinning. Loop it through here. All right, tie this off. What's going on there? All right, make a knot at the other end so this thing doesn't fray. All right. There's my finished zoetrope. So looks like. All right. How you guys doing? You guys doing all right so far?
Can you explain the string part again?
Yeah. All right. So talk about those last few steps again. All right. So just glance around the room again. It looks like everybody's a little bit different place, but that's okay. Right? So point you want to glue this around into a cylinder. It looks like you guys have got that figured out, I think. I glued into a cylinder. Right? So you got windows cut out, you got a cylinder shape. Right. Now the strings. Now what I did was I cut a bunch of strings that which I do recommend about 50 centimeters long. You guys have plenty. You're not going to run out of string. You've got plenty of string to do this. So this ruler is 30 centimeters long. So yeah, go 50. It's probably like almost 2 of these rulers long.
The length of the desk is about 50 centimeters.
Oh.
It's a little bit more, but it works.
Okay, yeah. So Morgan say the width of the desk is probably pretty close to what you need. So yeah, you do that. Okay, width of the desk. Now you guys want to cut 6 strings of that length. Right. Count mine really close. I have 5 strings that length, but that's all right. Okay. Then push the string through one of the windows and tie a loop around this top part right here. So you guys see how this is strung up right here, right? Here. Okay. Just tie it around, make a loop, tie it, and tie it off. Okay. Almost like you're tying your shoes, but then just make a double knot, like a square knot, and then that'll hold. Okay. Then go to the opposite window. Remember, you got a really long string. It's about 50 centimeters long. Okay. Go to the opposite window and do the same thing. Tie it there, okay. And then that'll give you it'll look like the handle of a pail. That's what it'll look like. Now, if you do that for all the pairs of windows, right? So pair. Got window pair, window pair, window pair, window pair, right? Just keep going around, right? That's how you get all these strings. Then after that, want to pull these all together and tie a knot so it makes like a cone shape. Right? See how this looks like a, see if I get this to spin around central axis, looks kind of like, these strings kind of like surface of a cone, right? So there you go. And I tied one more string onto it just to create a handle that I can hold, right? Then you get the thing to spin and see it from the outside. Got a handheld zoetrope. Right, that worked. Okay, so here's what I do. I'm gonna move on to the next set of demos, but you guys can keep working on the zoetrope. That's right. It said it'd take about 2 hours of materials and try to condense this down into a 90-minute block. So we got, but gonna make this work. Right, so how about here? Okay. Next thing, I want to tell you guys about reflection and refraction. I'm gonna sort of give you guys a mix of both. Let's start talking about refraction. though reflection's a little bit more straightforward, but you guys see a bunch of stuff by the end of the day. Right? You guys know what refraction is, right? Let's put my laser. So it's kind of, yeah, here we go. Okay. You guys know if you have a glass of water and you put a straw in the glass of water, the straw looks all bent out of shape, but it's not really bent, it's just an illusion, right? That's refraction. Show you guys another example here. When I have this laser light and I shine it through this prism, see how it bends? Like, there's some internal reflection going on. So actually, there's both going on here. There's the refraction is the bending part, and the reflection is it's going to reflect off the wall and refracts out here, right? But the light beam itself does bend. Right? Now, why does it bend? Well, there's a whole explanation with that I'm going to get to. Has to do with the fact that light slows down inside the material. So that whole idea about speed of light being 3 times 10 to the 8 meters per second, that's really only true through a vacuum. It's approximately true through air. Light travels a little bit slower through air, but not by much. But once it enters like glass or water, or, well, I'll probably call this glass, but I think it's actually some kind of plastic. It actually does slow down significantly. Yeah, Jared?
It's slowing you down. It doesn't have mass, right? So,
right. Yeah, so why does it go slower? One explanation I've seen is that it just interacts with the individual molecules, and as like plastic in this case. So as it does, then there's an energy transfer, but it transfers it interacts with each molecule individually, so it takes time to pass through space. Okay. All right. Now, I'll be interested in how did that light bend at one particular surface. So I'll measure this first, and then we'll look at the equations that match up with this later. So I'm going to create what's called a normal line. Now, you guys know normal means perpendicular, right? You guys know that in this class a long time. Okay. See how this dashed line is perpendicular to this surface? So this dashed line I just made is perpendicular to the surface. And I extrapolated it way out there, but sorry. All right, so that's the line I'm going to measure angles with respect to. You guys will see. I normally make this a whole lab. I'm just going to cut this down to like a demo today. Right. So I'm going to shine in this laser and try to track its, where does it go? Oh, you guys see it refracting out here too? Actually, this is probably a better example than what I did before. Right. So I'm going to follow this bullet of light. Looks like it's entering right about here, sort of, right? And then where does it go? It looks like it refracts. Try to get the right angle on this. So there's the bullet of light entering. It refracts, kind of like right out there, something like that. So that inside the prism, to get to that point, had to have gone this direction, right? So I got this versus this, right? Now, of course, after that, it refracted again and went out like something like that. But I'm just going to extrapolate this line. Right? Now, of course, it doesn't really go here. Actually, I'll even label this. I'll call this extrapolation. Right? Just say it was headed this direction, and had it not hit the surface, it would have gone on. Right? Like that. Right? So that lets me get 2 different angles that I'm looking at. I'm looking at this theta I, which I'm going to call angle of incidence, and a different angle, theta sub r, which I'm going to call angle of refraction. Right? I wonder if there's like some kind of relationship between these two, or why it would bend. Let's get some numbers on these. Where's my oh, Google Meet's still working. Oh, that was gonna blink out there again. Okay. All right, pull up a protractor. Let's get some numbers on these things, because we'll be able to do some of these numbers later. Looks like my incidence angle was, let's see, about, oh, is that like a 45-degree angle? That is like a 45-degree angle. Okay, so this is 45 degrees. It's random angles, just came out to be that. Let's see what the refracted angle is. All right, so zero out the normal line, swings through. Okay, now we have to go through extrapolation. Looks like 27 degrees. So 27 degrees for the refracted angle. Huh. So see, the angle definitely got skinnier going into the material, right? Wonder what this could possibly be related to. Okay. No, I'm gonna switch back and forth today. So we switch over to my computer. See, present screen 2. I've got a Paul Hewitt for you guys, where he explains refraction. Actually, Actually, you know what? Never mind. I changed my mind on this because I'll show you guys Paul Hewitt later, but just not this one. There's a reason I got to do this on paper anyway. Right? So I'll show you guys what he was going to show you anyway. If you want to see this video, you've actually got it on Google Classroom. Remember, I uploaded everything for you guys. Okay. Let's say we got these two different surfaces. Okay. Maybe I have air versus glass. Right? Or I could have air and water. Or I could have a vacuum and glass. Or right, just two different materials. Right? Where the speed of light is going to slow down significantly inside the material compared to air. Air in a vacuum, light travels about the same speed. Right? This is going to introduce an idea called an index of refraction, which I'll call N. So N equals, well, pick an equation here. So it's called the index of refraction. Right? This is a material property. It's equal to the pure speed of light through a vacuum compared to the speed of light inside the material. Right? Now, you guys know that the speed of light in a vacuum is as fast as light could ever go. It could only slow down inside the material, which means that this index of refraction, does it always have to be, see if you guys are following, greater than 1 or less than 1? Wait, hold on.
No, it has to be.
Greater than 1, right? It might be like 1.1, 1.2. Yeah. So it takes a little bit of thinking, but yeah, if the numerator is going to be the bigger number, right? So I wonder what it is for that triangle prism that we were just looking at. Right? I wonder what the index of refraction is. I don't know, maybe 1.5 or something like that. We'll find out. Right? Ooh, we actually do a refraction demo right here. You guys see the light like bending through the material? Right? See, right? You guys see that? Right. So, right. Well, let's see how it's going to work out, and then I'll tie it to this, and then show you guys something called Snell's law, which also involves that number. So let's say I have some incidence ray. Maybe I'll probably here. Right. So this incidence ray that is come down like this. I'll call this incidence ray. Not rag, ray. Right. Right. And then, okay, so it's going to be refracted, but why would it be refracted like you just saw? Well, this incidence ray, you guys know it's actually like a transverse wave. You guys remember how I broke out those polarizing filters a few weeks back and proved to you guys that light is a transverse wave? You guys remember that? Right. And these waves, these waves, that's one of them, has these wave crests. And what if I make a line at every single crest? So I've got crest, well, trough, crest, trough, or I could just go crest, something like that. Okay. Okay. You guys remember from crest to crest? That's called one wavelength. Call it lambda wavelength. Okay, you guys remember that? Okay. And do you guys remember an old formula that goes speed is equal to wavelength times frequency? Okay, you guys remember that? Speed equals wavelength times frequency. Right. Now, if light is slowing down as it goes from one material to the other material, which it does, right? Then this V is going to decrease, right? It's going to go from C to V, it's going to slow down. Okay? Well, if the left side of this equation decreases, then the right side must also decrease. Wouldn't that be true? Okay? But only one of these variables actually decreases between the lambda and the frequency. Okay? I'll show you guys that the frequency has to stay the same. I should have just done the crest. I just go back and maybe make these darker. Got crest. That's how I normally do this. Okay. Crest. Okay. And if I extrapolate to the right, maybe there'd be another crest right about here. Got crest. Okay. And then we could go on. Those could be the wave fronts. Okay. Now, if you look at the points where these wave crests are entering the water, isn't there a certain frequency that those wave crests are entering the water? Like blip, 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 right? Is that those dots right there? Isn't it true, or well, I said water, but I wrote glass. So isn't it true that the frequency that the wave fronts leave the air has to be the exact same frequency that these wave fronts are entering this glass, right? The frequency can't change. This number has to be the same for both media, whether it's on the air side of the glass side or the air side of the water side, right? It has to be the same, which means that the wavelength must decrease. Right? So if the speed's decreasing, the wavelength must decrease to satisfy that equation. Right? Right? And the only way for that to happen is for this light to bend. Let me show you that that's going to be the case. So by this light bending, it's called, in that bending as a physics term, it's called refracting. So this would be the refraction, the refracted ray. Right? See, if I draw a bunch of wave fronts that are perpendicular to that, they'd be like here, 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 right? Going like that. Right? If I extrapolate the other way, then it might look something like these. Right? But you guys see what just happened to the wavelength? Right? It got a lot shorter, didn't it? Maybe I could call this I and R, or 1 and 2, or not and F. However I do it, I've got two different wavelengths going on. Right? There was the initial value, right? And then the refracted value. And see how that also got smaller, just like this equation says it should. Right? Guess that? Right? But for that to be consistent, remember the rays are going perpendicular to those wavefronts. Right? Now I've got this refracted ray, and I've got, here's the angle of incidence, call it theta I, and here's the refracted angle, we'll call it theta R. Right? You guys see that? See, the refracted angle is really skinny compared to that angle of incidence. Right? You guys see that? Right. Ooh. Okay, so there's some refraction. Right, now let's go back to this demo that I did here with this glass prism. Right? And there's one more equation that I want to throw up here to tie this all together. How are we going to figure out this index of refraction? I'll go ahead and show you guys something called Snell's law. Snell's law says that index of refraction times the sine of the angle that it's on, that product is the same on both sides. Well, maybe I'll do 1 and 1, 2, 2. Right, so 2, sine theta 2. Right, so n1 sine theta 1 equals n2 sine theta 2. Oh, go. Google Meet's still working. Right. So if I know any three of these things, that between two indices of refraction and two angles, if I know any three of those things, I could solve for the last one. In this case, I do know three things. On the incident side, I've got air. Now, the index of refraction of air is very close to 1. For a perfect vacuum, it would be 1. Air is like 1.001 or something like that. So probably about 1. Maybe I want to know what is the index of refraction of glass. And the two angles I have because I just measured those a few minutes ago. So on the incident side, I've got a 45-degree angle. And on the refracted side, I've got a 27-degree angle. Right, guess that? So all I have to do is divide down. Let's see, what is sine of 45 degrees divided by sine of 27 degrees? That gives me an index of refraction of this glass of 1.56. Okay. Now that's my calculated value based on those measurements. So I bet the actual index of refraction of this material is probably like 1.5 or something pretty close to that, as I'm getting 1.56. Okay, guess that? Okay. Now, if you're thinking about think about this, the fact that those two angles are different. What if I tried out a bunch of different angles? What if I tried like 90 different angles, like 1 through 90 degrees? Right? There's actually going to be a very interesting consequence that falls out of that. Now, let me flip back to computer, present screen 2, share. Right. So I got some demos lined up for you guys. Let's check out. Well, I'll leave this guy muted for now, but I'll narrate what's going on. Snell's law. Oh, hey, that's what I was just telling you guys about, Snell's law. Oh, no, this guy has a semicircle prism, which is actually a really nice prism. Here's why. Because as long as he shines it straight through the center point, the light beam will only refract once. Right? It'll only refract at that plane surface. See, any light ray that's emerging from the center and going to the semicircle edge doesn't refract again because it's always going perpendicular to it, so it just goes straight from there, which is really nice. But he sets up a bunch of different angles. Maybe fast forward so you guys can see. You guys see how this is working? Right? Flip this whole thing. Let's go back to some of the smaller angles. Like every 5 degrees, he adjusted every 5 degrees and then get some measurements. All right, so you guys see this angle of incidence right here versus angle of refraction? See, angle of refraction is less than the angle of incidence. Okay, so you guys have seen that already, right? What about towards the end of this video? there's a couple of interesting phenomena that pop up. One is that this refraction is getting weaker and weaker, but look what's popping up. You guys see some reflection? Now, I haven't talked about reflection today, but talk a little bit about that. Reflection is actually a lot more straightforward because the law of reflection says that this reflection angle right here, also from the normal line, is exactly equal to the angle of incidence, as long as you're talking about reflection. You guys see this reflected ray right here, right? And towards the end, that reflection gets stronger and stronger, and that refraction on the opposite side here gets weaker and weaker. You guys see that? Right? But there's another thing that's really interesting too, and that's that this incident angle is approaching 90 degrees. You guys see right there, it's about 85 degrees, right? So it's getting about as far as he can take it. And this refraction, actually that refraction is really weak, you barely even see it. But let me back up a few more degrees. You see right here, it's like petering out at about 40 something degrees, right? And it can't really go much beyond that. It's running up against what's called the critical angle, okay? And you can do this in reverse too. Let me show you guys the video of what this would be in reverse, but right before I do, I want to point out something, which is that this refracted ray will never run into these angles far out here. Never will it? Right? So that, can you guys imagine if you were like an ant crawling around on this paper and you were on the flat side, let's say down here, nearby this incident ray, right? And you were trying to see what's on the opposite side of this prism, you would never be able to see anything that was like at the 20-degree mark, would you? Right? Because no rays of light would ever be attainable from that point. I was thinking last night as I was prepping for this class today, I was thinking, this would probably be really valuable information if you were like a magician, because you could probably hide some things in plain sight that just nobody would ever be able to see because they would be behind this critical angle. Right? Let me show you guys the next demo, which is the same thing, just flipped around. Remember before he was shining it in the flat side, right? Now he's shining it in the curved side. But you guys see the refracted ray up there at the top now is now approaching 90 degrees. Oh, right there, it just disappeared, went flat. But look at that incidence now. See, it kind of peters out at about 40 something degrees. Right, guys, yep, right. And if he does anything beyond that, it turns into what's called total internal reflection, because now there's obviously some reflection going on, but that's all that's going on. Well, there's a little bit of spread out refraction, but it doesn't really make anything very clean, right? It's all reflection beyond that, right? Yeah, so that'd be permanent hidden. Here's another application of this. If you're ever out fishing in a boat and there's a fish near the surface of the water, but maybe a few meters away from the boat, let's say it's like 10 meters out, but like 1 meter down in the water, that fish would be permanently hidden from your view. You would not be able to see it at all because of this right here, this critical angle involved in Snell's law. Right? Get that? So yeah, so pretty cool, right?
And just the way we compared it to when you're swimming underneath the water and you look up at the surface
Oh yeah.
and you'll see like all the light. And there's a certain angle where you wouldn't be able to see something directly above you. Not directly above you, but
yeah. Okay. Yeah. And then so Morgan's saying if you flip this around, let's say you dive underneath the water, you're like looking up. Yeah. There's only so far that you can see. Then beyond certain angles, let's say like yeah. When you're able to see some stuff, right? Yeah. So there you go. So that's right. So switch over and talk about reflection a bit. Now, I did promise you guys a Paul Hewitt, so let me find Paul Hewitt for this. Paul Hewitt's going to show you guys. Oh, I lied. Real fast. We'll do one more refraction, then I'll do reflection. Right. So you guys probably seen this, some version of this, right? Yeah. Pink Floyd album cover, Dark Side of the Moon. Right? Isaac Newton originally figured this out. Isaac Newton did lots of things, pretty much all or most of the physics that you guys learned in this class, and also calculus. He's one of the original discoverers of calculus. He also did work with optics and prisms, and he was the first guy to figure out that white light can actually refract into lots of different colors. And if you take those individual colors, combine them, they create white light, right? So each color has a little bit different wavelength. Red is the longest wavelength that we can see. Purple, like violet, is the shortest wavelength that we can see with our eyes. This is refracted at different angles, so you can actually get colors that spread out. Oh, here's that straw I was talking about. All right, but let's flip over and look at reflection. Now let's start with a plane mirror for reflection. Where is Paul? Ah, here's Paul Hewitt. Get my sound source switched over. He just told you guys law of reflection. Remember, law of reflection is real straightforward. If that's a 30-degree angle, then that's a 30-degree angle. It's that straightforward. Versus refraction, which is what I show you guys with the lasers, is a bit more complicated, involves index of refraction, Snell's law, but reflection, a lot more straightforward. Those angles are just equal. All right, now let's take a look at that. Now, he just showed you how reflection works for a flat mirror, right, for a plane mirror, okay? And no surprise, the image appears on the opposite side. That's called a virtual image versus a real image, which I'm about to show you guys too. And it's the same size, it's right side up, and it's the same distance from the plane, just exactly on the opposite side. Okay, so that's all fine and good. But what if you had some curvy mirrors? Show you guys a video demo on this, which if you're in class, I've got one of these so you can see this in person. One of the best. Yes. Now that's called a real image, right? And I'll show you guys how to do that. I said I've got that one in class, so if you're in class, you can actually see that. So stop sharing my screen. I'll flip over. All right. And I'm gonna do some ray diagrams with you guys. Some ray diagrams. Now, this is ray diagrams. Okay. Ray diagrams. Okay. If you're in class, then I gave you guys 2 of these pages because I'm gonna do one for reflection, and then later on I'll show you guys lenses and refraction. But I'm not gonna pick these up though, so these won't be for points. So if you're still trying to tie the last strings on your zoetrope or something, that's all right. Okay. So if you want to follow along, then feel free to, and happy to watch them. And I'm going to also do these faster than I normally do. So the first set, let's do reflection. Reflection. Right? This could be like mirrors. Right? And what I'm wondering is, where is the image? So here's what I could call the object. Okay. Now, Paul Hewitt had candles. A lot of textbooks use arrows. I don't like arrows as much because we're also going to have a bunch of light rays bouncing around. But I like stick figures, so use stick figures. Now, you guys see the first one is kind of like if you're looking in the backside of a spoon. You guys ever look in the backside of a spoon? You see a reflection of yourself, and you know what it looks like. You look kind of tiny, maybe a little bit warped, but you're right side up, right? So not super crazy. And so how am I going to get where the image is? Now I'm going to do something similar to what he did, but it's going to be for a curved mirror. All I have to do is follow a couple of light rays. Now, in reality, there are like a bajillion different light rays bouncing off the sky, a bunch of photons bouncing all over the place. All I have to do is follow a couple of them to figure out where his reflection is going to be. I'm going to go, one light ray is going to be, let's go top of his head, just like probably at top of the candle, parallel to the ground. See, it's like parallel to the ground. And it's going to bounce off the surface, boing. I think it's going to bounce probably kind of up and to the left. But where exactly up and to the left? Well, that depends how curved the spoon is. That's why I have this focal point. That's what F stands for. It stands for focal point. Okay, is that focal point? And this distance is called the focal distance, which I'll show you guys an equation later, but for now, let's just do ray diagram. So if I go from the focal point to that point where it's boing, bouncing off the mirror, see it go like this? Now, of course, no light actually goes on the right side of the spoon. It's just extrapolated to the right. That's really all that's going on, right? Boing, right there. Is that? So that's one ray light. Okay, so that's all fine and good. How about another ray? What if there's a ray of light going from the top of his head straight towards the focal point? Of course, none of it really crosses the plane, which is anything to the right of the plane, just extrapolating, right? What it will do is it will boing, bounce off back parallel to the ground. Okay. Again, I want to extrapolate back to the right, and you guys will see why here in a moment. Okay. Because those two rays of light, the original boing and the second boing, they meet up in two different places. They meet up at the top of his head. They also meet up behind the mirror right here. So that would be the top of his head. If I did all the same thing for his feet would still be on the ground. So I'll throw his feet on the ground. Oh, yeah. Thank you, Kevin, for grabbing that. Okay. And this would be the image. Okay. Now, the fact that it's on the opposite side, just like usual mirrors, this is called a virtual image. Okay. And you see it. Oh, that is what you see on the backside of the spoon. You see an upside version. Right side up version of a smaller version of yourself, right? What if you were to back up away from the spoon, or if you had a more tightly curved spoon, which are kind of the same effect, right? That's what the second one is, which probably won't be a whole lot different from the first one, but let's just run it and find out. Remember, one ray of light goes parallel to the ground, top of his head. It's got a boing bounce off, such that it would cross through the focal point. Could somehow break this plane. So this is my first ray of light, boing. Now, next ray of light, and you go from top of his head, headed straight towards the focal point, but it's going to boing bounce off the surface back parallel to the ground, extrapolate to the right, and these lines meet up over here. Oh, look at this. Here's the image now. Now it's really tiny, right, versus object. Right, is that? Right. And if you back up a spoon away from your face, then you're going to shrink really fast. Right, this is from here to here, right? How about the third one? Now, the third one, I was trying to get something pretty close to a plane mirror. Notice that the closer the focal point is to the surface, that means the more tightly curved the curvature is, right? Versus if the focal point were infinitely far away, like 10 miles away, then that would be a plane mirror. So this bottom picture isn't exactly a plane, but it's as close as I could get because that's probably as large a focal distance as I could have, just the width of the paper. Let's do that same method. Now, you guys know what a plane mirror outcome should be. It should just be same size, opposite side. This should approximate that. So first ray parallel to the ground, where it is bouncing off that mirror surface, I'm going to have to go through the focal point. So this mirror does have a slight curve to it, but only very slight, right? Or maybe it's like a huge sphere or a huge spoon, right? Another ray of light go from the top of his head to that focal point. And then it bounces off the mirrored surface back parallel to the ground. That's right about like this, right? And then where those two lines meet up on the opposite side, that's like right here. Okay. And look at that. He's about the same height, about the same size. He's also about the same distance from the surface, just on the opposite side, just like you would see for a plane. Is that? Right. Okay, so that's for convex mirrors, and convex mirror is pretty close to plane. Okay. What about for concave mirrors? Notice that here I've turned around the spoon. You guys see that? Turn the spoon around. Now we're looking at the inside of the spoon. All right, so let's do the same method. Now, these are going to turn out pretty different, but same method though. So here's one ray of light parallel to the ground. It's got a boing, bounce off the mirror through the focal point, like that. How about another ray of light that actually goes straight through the focal point? That's going to boing, bounce off parallel to the ground. Notice where those two meet up, right here. Here's the top of his head. His feet, long story short, are still on the ground. And oh, look at that, right? So here's the object, just like it's been all on. Here's the image. Now this is called a real image, right? Because notice it's in front of the mirror now, just like that pink pig. This is how the pink pig illusion works, right? Looks like it's hovering in front of the mirrored surface. It's also inverted because he's upside down. So it's real and inverted. And that pig, if you look really close, it actually just flip it around backwards. Okay?
So if you're like standing on top of glass, you would see like a small version of yourself walking on the bottom.
Yeah, you can actually try this out too. So I can't really get this to work on camera, but here, let me show you guys. So I do have this flying saucer pig in here, and so this does work. But you can pull this apart, and you can effectively get these concave mirrors. I should pass these around. You guys can put this in front of your face. You can try this out. If you get this pretty far away from your face, you should see an upside down version of yourself. Looks kind of small, looks kind of hazy, like you're kind of floating in space. It's kind of weird. So get that passed around so you guys can see that. Okay, but what if you do this though? Hold on, gotta refresh this.
Actually, Google Meet's been doing better this class than last class, so doing better. Right. What if you got that parabolic mirror really close to your face? Right? You guys ever use a cosmetic mirror? Right? Blows up your face a little bit. Right? That's actually what this bottom picture is like. The top picture and bottom picture, the only difference is the top one, your eye is outside of the focal distance. Here's the focal distance. Right? Right. First one, you're outside that focal distance. The last one, your eye is inside the focal distance. That's the next one I'm going to do. I'll come back to this middle one, but not quite yet. Let's do the same technique. So I'm watching this light bounce around. Yeah, we're talking about reflection, right? So ray of light parallel to the ground, it's going to reflect, boing, to this focal point. Now here I'm going to extrapolate to the right. You guys will see why in a moment. Right? Now another ray of light is going to, from top of his head through the focal point, it's going to bounce off the mirror right there, boing, back parallel to the ground. I'll extrapolate to the right, just like I have been all along. Right? And you see where they're going to meet up over here? Right? It creates a virtual image. We're back to virtual because it's on the opposite side, just like a regular mirror, plane mirror, right? But this time it's blown up a little bit, like a jelly green giant. Yeah, Morgan?
So we were talking about the cosmetic mirrors in Gentile's class last semester, where there's a certain point where you go from enlarged to upside down. We were trying to figure out that point, but he said it zooms in so much that it's really hard to tell. Like you can't just like.
Yeah, kind of good questions here. It's like, how do you figure out? Because all these pictures on the back could be referring to the same mirror, but maybe you're getting completely different outcomes depending on where your eyeball is, right? So can you figure out where this focal point is? Let me see if I can get this to work on one in front of me now. I do have a cosmetic mirror right here, but it looks like the focal distance is pretty big. It's longer. The focal distance of this mirror that I'm holding onto is longer. Okay. What if you put your eye right on top of the focal point, which you guys can probably do with the parabolic mirrors with flying saucer pig, pull that apart. Now this one has a really weird outcome. I'll show you guys what it is. I mean, what's halfway between this and this? Let's find out. So same method. Got one ray of light, top of his head, parallel to the ground. It's gonna boing, bounce off the mirrored surface to the focal point. Okay, so that looks all fine and good so far, right? No problems. But then remember, there's one ray we've had going from the top of his head through the focal point, and okay, well, now we kind of hit a dead end, right? Kind of blows up that point. The answer to this one is that there is no image, right? So if you have a cosmetic mirror or that parabolic mirror, flying saucer with the pig that you pull apart, and you put your eye right on top of the focal point, you will just see a blur of light, but you won't see, either upside down real image or right side up virtual image, you won't see either one of those. You just see a blur of light, okay, where it like transitions. Yeah, so that's that. Okay, that's that. All right, now there is a fun equation that goes with this. You guys want to see the algebra equation? It goes like this. 1 over the focal distance is equal to 1 over a distance object plus 1 over distance image. Okay. This algebra equation explains, you could predict where is the image going to be for every one of these. I'll show you guys how. Let's say I'm going to pick this one right here, just at random. Pick this one because it works out. Right. Now, where's the object, where's the image, and where's the focal distance? Right. If I know any two of those, maybe I can solve for where the image is going to be. Right. So let's see where the object is. The object is, it looks like about 6.5 centimeters from the surface. You guys see that? 6.5 centimeters. Right. So I'll put the object out here at 6.5 centimeters. Right. So that's that. Right. Now the focal length looks like it's 3 centimeters. You guys see 3 centimeters, but it's also on the opposite side, and I have to. Okay, so the fact that the focal point is on the opposite side, I'm going to use a negative sign, so I'll call that -3 centimeters, right? And then, you know what? I'm going to solve this algebraically. Okay, so let me pull the calculator, solve this algebraically, and then we'll see how close, because the ray diagram method and the algebra method should be the same thing, right? Just two different points of view. Let's try this out. So 1 over -3, right, minus 1 over 6.5. Now this would be 1 over the image. Isn't that true? So if I take the reciprocal of that, so 1 over that, shouldn't that give me where the image is? And the answer is -2.05 centimeters. You guys see that? -2.05. So negative means it's on the side of the focal point, which is definitely true. 2.05 centimeters. Let's actually measure this with a ruler. Hey, that's exactly where it is. It's like a smidge beyond 2 centimeters to the right. Right? That's exactly where the image is, which is exactly where the algebra says it should be. Right? Guess that? So now you guys have two different ways to find where the image is for a mirrored surface. Right? Use ray diagrams, or you can use the algebra. Right? Guys got that? Okay. Then now, if you're in class, you have a completely different ray diagrams page, which looks exactly the same, because this one I want to do some refraction. You guys ready to do refraction? Okay. Again, I'm not picking this up for a grade. This is I'm also doing these faster than I normally do. Right? Refraction. Okay. Now, refraction. I'm going to turn these into lenses. Right? You guys know. We'll start with some converging lenses on this side. You guys see some converging lenses? No, rules are a little bit different, but I'll show you guys how you'll find the image with this. Let's follow one ray of light, top of its head parallel to the ground. Right? It's going to refract through the focal point. I'm going to extrapolate to the left. You guys will see why in a moment. Now here I've already made a sort of a shortcut. It technically refracts twice. Once from the air to the glass, and the second time from the glass back to the air. But get sort of cut through that. Okay, that's it. All right, and then here's a rule that's unique for refracting lenses. Is I'm going to have a line that goes from the top of his head through the center of the lens. Right, and see where it meets up back here. So object. Okay, so what I just showed you, you know what this is? This is a magnifying glass. So if your eyeball was over here, you're like, looking what's going on. Ooh. Then this could be your magnifying glass. This could be what you're trying to magnify. And then to your eyeball, it would appear like, it gets blown up really big, and that's right side up. Yeah, you guys ever use a magnifying glass? Okay. That's what that is. Okay. What if you, remember the second one's pretty similar to the first one, except it looks like maybe we're like backing the magnifying glass up a bit, maybe something like that. Right? So what if you back it up away from the page? That's going to happen. What's going to happen here? So let's use the same method. So ray of light parallel to the ground. It's going to refract through the focal point. Then a third line is going to go through the center of the lens. Right? Ooh. Now for the mirrors, there wasn't a whole lot of difference between the first two. Remember, backside of a spoon. If you look at the backside of a spoon, then you can pretty much only get one outcome. But for the lenses, completely opposite case. Actually, this does look like a real image now, doesn't it? Right? Do something like that. Refract out the other side. So that's weird. That's interesting. What about for something that's pretty close to a plane? Right? Now, a plane lens, I wouldn't think would be much different than. Actually, this is probably pretty close approximation to what we're about to do, right? Just like a plane refraction. Right? It's probably not a whole lot different than what's already there, but let's see if we can confirm that. So line there, ray of light, see, through this focal point. So there's the boing, first ray of light. Right? Then remember I need a ray of light that goes from top of, this is the refraction rule, top of his head through the center of the refracting lens, right? And remember, this is maybe not a perfect plane, but it approximates it, right? Look at that. Look at where the image is. The image is basically where the object is, right? I mean, tiny bit different, but you know, so if you have something that's refracting but has a slight curve to it, probably not going to change it a whole lot, right? That agrees with that. Right? Guess that. Okay. How about now? All the ones we just did were for converging lenses. Right? How many guys are farsighted? Anybody here farsighted? Farsighted? Right? If you're farsighted, then you're probably wearing glasses that look something kind of like this. Right? Versus, if you flip this page over, we're about to do some diverging lenses. How many guys are nearsighted, like me? Yeah, I think I saw there was some theory that when people started, there became like mass literacy, which is only true in the last couple of 100 years. Just like when you stare at pages like all day throughout your childhood, that makes people tend towards nearsightedness. Versus if you go back like 1,000 years ago and nobody was reading any books, then your eyes would develop to actually like see the world. But let's make some diverging lenses to look something kind of like this, right? Diverging. Except now we're going to use the same rules, but get different outcomes now. Notice that the focal point is on the opposite side. It's just a different way of defining it. And so ray of light, top of his head parallel to the ground. It's going to refract sort of like that. And then I need a ray of light that goes through the center of the lens, top of his head. So, there you go. So there's the image right there. So that would look like. Interesting. How about this middle one? Now remember this middle one before, for the mirrored surface, for the reflection, I skipped it and came back to it and created no image. Right? That's not going to be true for the lens though. The lens, see what happens with the lens. So here, and then top of his head through the center here. Look at that. The image looks like it's going to be exactly halfway between the object and the lens, right? And then what about the last one, where you get inside the focal distance, inside it, right? So there, and then top of his head through the center, there, boom, boom, boom. Here's the image right here. So there you go. There's the resulting for diverging lenses, right? Yeah.
When I was little, like in third grade, whenever I was bored, I would take my glasses and make people think small. It was funny.
Yeah, pretty funny. So there you go. Yeah. Now explain. I make got shrunken head enthusiast in here. All right. Let me put my screen back over and show you guys if you put this all together what you can do with this. Because I showed you guys, some reflection, some refraction, show you guys Snell's law, show you guys the algebra equations for this. Present my screen. Right. So what technology can you make with this? Oh, probably like a telescopes and microscopes. Is that what you guys are thinking? Telescopes, microscopes? Yeah. Let's take a look at those.
Your eye is controlled by muscles that change the focal length in order to focus on objects at varying distances. The incoming rays that enter through the cornea strike the retina at the back of the eye. The retina acts nearsighted. In this case, the eyes make light rays converge too quickly, causing the image to form too far in front of the retina. So nearsightedness can be corrected by diverging lenses, spreading out the light rays so a focused image is formed at the proper distance. But lenses can not only correct problems you have with your vision, they can also produce images of things that would be indecipherable to anyone, no matter how good their eyesight is. Let's start small and take a look through a magnifying glass. Any simple magnifier consists of a single converging lens, which produces a virtual image that enlarges an object. And you can use a trusty ray diagram to show how this image forms. If you had, say, a small leaf that you wanted to inspect, you just put the leaf inside the focal point of the magnifier. Since the leaf is inside the focal point, the rays diverge and the lens forms a virtual image that's much larger than the original object. And ideally, this virtual image forms just past your near point, because if it were closer, you wouldn't be able to focus on it. Now, you can measure a lens's magnifying power by comparing the angles at which light rays enter your eyes. Every object takes up some amount of your field of vision, and mathematically, you can express that in terms of how much that object subtends. An object is said to subtend a certain angle of your vision based on how close you are to it and how big it is. For example, if you're looking up at the moon and you cover it with your thumb, then your thumb and the moon are both subtending the same angle to your eye, which we measure in degrees. So if you look at our tiny leaf, it may subtend only 2 degrees of your vision when it's at your near point, say 25 centimeters away. But when you look at the leaf through the lens, the virtual image is larger than the actual object, so it subtends 6 degrees of your vision. In order to find the magnifying power of the lens, you just divide the angle subtended by the virtual image by the angle subtended by your unaided eye. This equation, which holds true for all magnifiers, tells you that this particular lens has a magnifying power They can have huge openings, taking in as much light as possible in order to best capture images of distant objects. These mirrors are convex, causing rays to converge into a real image, which is then magnified through an eyepiece or projected directly onto a digital sensor. Now let's switch gears and shrink back down to the small stuff. A simple magnifier isn't enough to study objects on the cellular scale, so we've developed compound microscopes, which, like a telescope, use objective lenses and eyepieces to magnify again form a flipped real image on the other side. And just like with telescopes, the real image is just inside the focal point of the eyepiece, generating a large virtual image for the observer to view. Now remember, for all these optical instruments, our original optics equations still hold true. We have the magnification equation expressed in terms of subtended angles, but we can still use the equations in terms of distance and height for both objects and images. Likewise, the thin lens equation is still applicable to most of our basic situations. Remember that? It's the equation that relates the object distance and the image distance to the lens's focal length. Now, as a laser result technology is becoming capturing images, we can't escape the fundamental wave nature of light. So when we first learned about how light travels as a wave, we saw how light passing through a thin slit spreads beyond the edges of the slit. This diffraction, which is the reshaping of light by obstacles, happens in lenses too. Since lenses have edges, the incoming rays will always diffract and produce slightly blurred images, even if the lens is perfectly crafted. For instance, a single point of light when captured by a camera will appear as a central bright spot known as a diffraction disk, with weakening circular rings of light spreading out from it. The ability of a camera to produce images of points very close together is called resolution, a term that you've probably heard before. As the magnification gets higher, because the diffraction patterns that they create are magnified too. So the magnifying power of optical tools is limited because light acts like the wave that it is. Today we learned about how the human eye functions like a camera. We also studied.
All right, yeah, so Crash Course Optics, if you want to check that out, that was worth your time there. All right, so yeah, let's walk around and check out you guys' zoetropes. You guys did a really good job on those. You guys had some really imaginative animations and together really well. So nice job there. All right, got some puzzle questions for you guys. Well, somewhere I do. Here they are. Right. Puzzle questions. Okay, so these are all related to mirrors. Did she mention who invented the reflecting telescope? Right. Because she did mention that for refraction. Why is it nice? You mention that for refraction, you're always going to get a little bit of a blurred image just because, well, she mentioned a different reason, but one of the reasons is that the fact that it does refract twice, right? It's got to be some thickness to refract twice, right? Say if you've got a refracting telescope, you're trying to look at Jupiter, right? The color's going to spread out a little bit. You get a little bit of a blurred image. Isaac Newton figured this out. He said, "Oh, if you have a reflecting surface, then you don't get that refraction blur." So Isaac Newton actually invented the reflecting telescope. It's a different kind of telescope, gives you a clearer image. Right, so speaking of mirrors, got some mirror questions for you guys. Start with this one. Pretty fun. Zoom in for you guys in class. Oh, what's happened to good stuff? All right, so. Got this lady here. Oh, we just start with the pronoun she. Got a mysterious she stands 1 meter in front of a dresser mirror. So 1 meter right here. And is looking at, she's trying to see this flower on top of her head in a small mirror 1/2 meter behind her head. Right? How far behind in the back of the dresser mirror does she see the image of the flower? Now, the premise here is that she can't see the direct reflection of the flower because it's sort of on the back of her head. Maybe they should have drawn the cartoon that way. Okay. But she's looking at a reflection of a reflection, right? So the flower's getting reflected in the little mirror, the handheld, and then after that, that reflection is being reflected in the dresser mirror. And the question is, if you start from the plane of this dresser mirror and work backwards from there, how far back does she see the reflection of the flower? Right? How many meters? Who thinks they can figure that out? What are you thinking? Oh, Eric's saying 2 meters. Good call, because that's the answer. And yeah, not a whole lot of students get that, so that's really awesome if you're thinking 2 meters. So good call. Right, so the way you'd want to solve this is to start with, you should color the sun, sort of, it's red color. Okay. Start with a handheld mirror. Wouldn't the reflection be 1/2 meter back behind this mirror, like probably right about there? Right, that's 1/2 meter. That's 1/2 meter. Right? 50 centimeters. Right, true. Right. And then the dresser mirror is now getting the So,
can the screen, right? Right. So yeah, the fact that this is 2 meters here, she would also see the reflection 2 meters back. That's the answer. 2 meters. So good call. Okay. How about oh, here's one that you guys can try some point one day. Okay. You guys see this guy standing in front of this tall mirror that looks about the same as his own height. Now, do you think you can see his full reflection here? Yeah, he can see his full reflection. Let me try to draw. He's got this weird shaped head. It's kind of stand sort of like this. Feet down here. It's kind of this. How's reflection going on, right? Something about like that. It's got some hair going on. Right. And the question is, what's the minimum size for a plane mirror to be able to see your full reflection? What's the minimum size, right? And we'll start with these last couple of options because maybe intuitively it might seem like it's a couple of these, right? Do you think you would necessarily need a full height mirror to see your full height? Okay, so I see you guys shaking your head. So you're right, it's not that one. Do you think that it depends on your distance? Like if you get closer or further, do you think that the amount of your reflection changes in the mirror? Right? You're right, it is also not this one, which is not intuitive, or at least I don't think it is, right? But guys, try this. If you're ever in front of a very large reflective surface, I know I've done this at like an airport terminal at night when it's dark outside and the walls turn into mirrors, right? Look in the reflection, and see where's the top of your head. Oh, nope. Google Meet's still working. And where the bottom of your feet, and then back up away from the surface and get closer to the surface. And it have you marked on the mirror where those are? Maybe put a little piece of tape here, put a little piece of tape here. You know where you see your head and where you see your feet. It doesn't matter how close or far away you're standing. Right? Oh, I passed around that cosmetic mirror. If you guys back up and get closer to that cosmetic mirror surface, the amount of your face that you see does not change. Weirdly enough. So, so how much mirror, to actually answer this question, how much mirror do you need to see your full self? Well, let's look at, let's go from his eyeballs and see. For him to see the bottom of his feet, that'd be like some ray that would do something like that, right? Oh, whoops. Got to back up for the class, right? Now, really, of course, it's the boing bouncing off the mirror. There's the actual bottom of his feet it's going to, something like that. And then the top of his head, he would see emerging from this ray of light, which actually the boing bounced from, something to do with that, right? The boing, right? Look at the actual amount of mirror that he needs compared to his full height. What is this distance compared to this distance? What does that look like? Pretty close to. You guys saying half? Let me measure it. This is about 2 centimeters. He's about 4 centimeters tall. As if he's 4 centimeters tall, and this piece of mirror that he needs to see himself is 2 centimeters. You guys see the answer is going to be half? It's going to be half? Yeah. So if you are like 2 meters tall, you only need a 1 meter tall mirror to see your full reflection. Now the catch is you have to put it in exactly the right spot to see yourself. Put a piece of tape here, piece of tape here. He backs up away, sees the same amount of himself. Right. Oh, yeah. Right. And hold on, what just happened here? I got to.
all right, so we're back. I think we can fit in one more for the bell. All right, this question. Did I tell you guys about this back in the day?
Not back in the day, but like we was just mentioning this exact concept.
Right. Yeah, you're right, Jerry. We did just talk about this. So to see more of her face, let's say she can only see like 80% of her face. And I want to see more of my face. If she holds it closer or further away, makes no difference. She needs a big. All right, Google Meet is really wigging out right now. So but let's call that a day. So everybody online, thank you for being patient with Google Meet. I know it's been not working very well. You guys in class, have a good Monday. I'll see you Tuesday, and we will do fun stuff.
Oh, Mr. Griffin.